Okay, welcome to this lecture note. Our class will be recorded through this Zoom. Again, we have chapters from 1 to 14. Now, since this class is the second part of solid mechanics, I would like to go through all the chapter and make sure what subject should be or will be covered in this class. Well, chapter 1 is the analysis flow. What is the analysis flow? When we solve the problems of solid mechanics, I will double check what the subject is all about. The solid mechanics. There should be, where some mechanical engineers are complaining or some have a hard time to understand solid mechanics. But it's not that difficult subject. As long as you understand the flow, concept flow, and concept structures, which is very important. So I will introduce that flow analysis or chart, and then all the subjects which we will follow will be based on that flow chart. Well, I will better use this analysis flow for solid mechanics. Again, this is not just the one of a slide. This is the those most fundamental flow charts in understanding solid mechanics. And I'm not just saying that. I'm going to follow this on the left-hand side. You have 1 to 3 subjects: force, materials, and deformations. And the middle, we have an equilibrium and the stress less than strength. This is sometimes called the failure criterion. Stiffness and strain and deformation condition. On the right-hand side, we have a strength subject. Okay. Now, today's, again, first class, but this is the one flow chart. 1 to 3, 1 2 3 4 5, 3 5 1 flow. Okay, I'm going to call this flow 3 5 1 flow chart. Okay, and just remember that. Okay, memorize that. 3 5 1. What is the 3? Again, the force. I'm sure you have a little bit of a concept of a force. Sometimes concentrate, sometimes distribute, sometimes a moment, any kinds of physical quantities which can be applied to a certain object. So anyhow, force and materials. What is the materials? Well, well, it's a very broad concept, but materials is the one you can touch, you like to understand. You can design some materials like a steel, aluminum, or plastic, any material which we are using to make some products. And deformations, deformation, deform. Okay. So the force will apply to materials and material will deform. Very clear concept. The force will apply to material. Say this is a material. We are applying the force, and this material, what will happen? Will deform. Okay. This is the 3 subject we need to start with. Again, 351. This is three concepts. You can imagine, you can visualize anything. You can, to better understand this subject, you can say, imagine a car or bridges or airplane. Anything will be okay. Let's say airplane. Airplane itself will be a material. What is the force? Well, the force will be from all the lifting force, from the pressure difference. That's the force. And then what will be the deformation? Well, the wing will slightly deform like this, which is sometimes difficult to see that, but there is always a deformation. Even the car crashing, or driving, or bridges, anything. There is a object, materials, and apply the force, then materials will deform. Okay, so this is the three concept out of 351. So we're gonna start with learning what is all about the force. Where force can be again the concentrated load, or distributed load, or moment, or twisting moment, or bending moment, all kinds of load, which are mainly covered in statics. And materials, again, the steel material can have a sort of a geometry, and is in there, you would have all the material properties, say stiffness, or the Poisson's ratio, all the, let's say spring. A spring is very easy to understand. Spring has, there's a spring, we apply load, and then the spring will deform. So spring itself will be material, and the force is the force you apply to a spring, and what happened to a spring will deform, right? It's a very, very simple. I'm not going to give you this class, as I said, very easy. So this is the force material deformation. Again, right now, I'm trying to help you how to, or what to memorize. And as you can see, these three things is the kind of external physical quantity. The force is outside, and material, you can see the outside, and then deformation, you can see outside. Now, the second, oops. What is this 5 flow? This is something inside material. This is something inside. Material has some stiffness. Stiffness means that you have some spring constant. F equal Kx. F Kx, right? So K inside is characterized or denoted as a spring constant K. So we have a stiffness. And then stiffness inside, there is say stress. Now the spring cannot well cover the subject like the stress strain. So let's extend the concept of the spring to a bar. Okay, it's a bar, long bar with some cross sections, and easy to follow the concept. Same concept as a spring. Now we have a bar. Again, the bar at the end, we can apply the force. We can, this bar will deform. And this bar, inside there's a material property, stiffness. Inside material, there will be a force occur inside the material. These are called stresses. Okay? Outside the force, we don't call them stress. Always the inside, there will be some internal force, they are called stresses, stress. Okay? And these stress do not just freely exist. There is always a physical law or rules which governs how those stress exist in material. That is called equilibrium. Even external force, let's say we apply the load like this force on the right-hand side and left-hand side will be equilibrium. We have a bar, very similar to a spring. We have a force, and it's a K, and this will be also K. And now this will be a deform, some deformations like this. And same to this bar, we have a force, let's call a P. And then this is a kind of, now is a kind of a solid, rather than just a spring. And inside, okay, inside, if we look at the inside, this something will happen. Something will happen. Imagine that this bar, consider your arm. Somebody will stretch your arm. What do you feel? You feel a little bit of a extension or pain inside. What caused that? Because internally there is some forces occur, and those are called stresses. Okay, so again, the stress is the same, very similar concept as a force, but the internal force you call stress. Now there is it says it should be less than strength. What does it mean? Imagine somebody stretch your arm and you feel pain, but if you say the force is exceed your strength, what will happen? Your arm will be broke, right? That should not happen. But every subject, every material has a certain limit in terms of a stress. So if the stress reaches that certain limit, the material will fail. So that limit is called strength. So strength and stiffness should be given, or should be some material property of this subject. Okay, so strength and stiffness, those are two physical quantity which characterize the material. So I'm sure you see the this curve, stress strain. You know what it is, and the P. This is a cross section, while the stress we often call P over A, because P itself can be very large with a very thick bar, or the cross, depending on the cross section, the way the material field will be different, even large force or small force. So always the with respect to A is important, right? P itself cannot, and it's not a proper way to describe how much what's happening inside the material. So the stress is like that. It's the force per unit area. So that's the force, and now the strain is let's say this is a length, and this is a extension as a delta. Again, it will deform, but imagine that 1 meter extend 1 centimeter, or 2 meter extend 1 centimeter. There's should be some different feeling, right? So the whatever displacement itself is not a proper way to describe the deformation. It has to be some with respect to the length. So 1 meter, 1 centimeter. Another 1 meter, 1 centimeter. That means the 2 meter, 2 centimeter will be the same as the 1 meter, 1 centimeter deformation. 1 centimeter, 2 centimeter cannot describe the deformation. So that's why the strain is always a delta over L, deformation with respect to length. Okay? And then again, when we apply this some load or stress, there will be some stress strain curve. And depending on the material, let's say steel or aluminum, even rubber, we have a different slope. This slope doesn't need to be linear, can be a nonlinear, can be any different complicated curve, but most likely the structural or material which we are using to design some material is always a linear. And then this slope will give us the very important understanding of this material. Imagine there's a steel extension or just the rubber extension. Same amount will, will give us different deformations. So stiffness is like that. This is the stiffness, Young's modulus, and stiffness E. Speaking about the strength, okay, speaking of strength, as I said, if this stress level reaches certain level, say yield or strength, what will happen? Material will fail or break. Okay, so this is the strength. Equilibrium, again, very simple. Let's say there is if there is some P there should be some reverse at the same magnitude P with a different direction. So this P plus and this P minus, so equal 0. That's the condition of equilibrium. Otherwise, the material, let's say you imagine the force on the only one side. This object will move. That's not the subject we cover in solid mechanics. That's the subject we cover in dynamics. So all the forces which are applied to the object will be or should be in equilibrium to be stationary. And not only the external force, but the inside, the same thing. If you look at here, all the load inside, this will be all equilibrium as well. So this equilibrium will govern this stress, and then stress has some stiffness. Now we deform, that is called strain here. And strain, okay, even strain, they don't just deform by themselves. Let's say you have a body and then deform. It cannot deform like this, right? Deformation has to follow or some constraints when it happens in a body. So that is the deformation condition. Even for the say wing, airplane. If we have some, some force here, if we look at here, that deformation means that this parts connect to the fuselage will not move. That is a deformation. So again, any subject, let's say somebody will extend my arm to outside, the deformation condition will be this shoulder is the one, this is where my arm is attached, right? So this is the deformation condition. Okay, so this is the 5 subject which will govern what's happening inside the material. Very simple. I know, I'm sure you already went through this all the subjects. And those are 5, and on the right-hand side, there's a strength. So even in, okay, so this is a 351. Again, on the left-hand side, this 3 concept is this sort of external load applied to a solid, and then what's going on inside. There will be a material stiffness, and upper there will be some stress, some equilibrium, and down there the stiffness was relating stress and deformation, right? So deformation and deformation condition, and there is another material property as a strength. Well, this is a not difficult subject, but this is a very important guideline for us to follow to deeply understand solid mechanics. What I mean by deeply is that now stress can be 1-dimensional, 2-dimensional, or 3-dimensional. So we need to define sigma xx, yy, sigma xy. Why you need two subscripts? Well, no matter each subject, how complicated it can be, you should not forget global map or guideline. Don't be get complicated by local subject. No matter how complicated it is, this you need to have a clear picture of this global flow, please. And even the strength, well, strength in this case, we only have a sigma y, but in 3-dimensional body, you have all kinds of stresses, and now you have a failure criterion or von Mises stresses. Those are stresses control the material failure. But again, even though this becomes the 3D dimensional or 2-dimensional, for that purpose, you need to understand Mohr circle. Well, that's the subject we're going to cover this semester. So anyhow, this is a 5 subject you should remember. This is the homework number 1. Just the flow, draw yourself again, this flow chart. Very silly, but just from the blank slide, you write down. I recommend you to use always handwriting rather than typing. Okay. So in PowerPoint, when you submit the subjects and the slide, it's perfectly okay. You can use a handwriting. Well, if you don't have a digital, pens, it's okay. You just use a piece of paper with your pen and pencil. You have a capture and upload to a slide. So anyhow, I don't care much about the format, but more importantly, to get yourself into the understanding of essence. Okay. So we just keep okay. Well, 5 minute break. Okay. Okay. These are again we call 351 flow chart, guiding us to understand the flow of the solid mechanics. Now again, with this flow chart on, this is the same slide. I will quickly go through how our lecture note consists of. Again, the analysis flow, we have a full slide describing of this main flow chart and what kind of materials we're going to cover. Here we said the materials, right? So in this class, we're going to cover bar. Bar means it's just one-dimensional long slender body with a certain cross-section, relatively long structures. That is called bar. And the force we apply usually the extension load. And then, as I mentioned, we have a 5 flow. And then what about the 5? Each category, you have it. Let's say we don't know, we don't have to know yet, but this is the flow. Apply this 5 concept to any body, any materials. And the shaft, this shaft, almost the same one-dimensional structures, but the not because of geometry objects are different, but the force applied, this force now is applied differently. Let's say an extension, you apply the twisting. Then the structure is called shaft. And then another one is a beam. Same one-dimensional, but at the end, rather than extension, rather than torque, we apply the bending moment or vertical bending. So that's why we call the beam. So this in this class, we usually cover one-dimensional structures with a little bit smaller cross-section with a relatively long structure. That is the one-dimensional. Not exactly one-dimensional. This is a still three-dimensional, but the major wise, we have longer structures. So again, depending on the forces, we'll call them bar, shaft, beam, 3 main structures. And this is all the theory we cover. Okay, again, I'm not gonna go in detail. So that is all about the analysis flow. Hmm. Uh, Just one second. man. 지금 혹시 그 줌으로 들어온 사람 있어요? Anybody join as a Zoom? Please check your screen. My teaching assistant. 아, okay. You just the Jiming, Sun Jiming is the graduate student, PhD. Actually, he got the PhD this last semester. Now he's a doctor son who will be in the our Kakao group. And so if you guys have any, or you cannot contact me, and please feel free to contact him and ask any questions. Okay, so as you can see, we have this is a chapter 1 describing all the flow chart, and then force equilibrium. Okay, why and what's this force? Well, force corresponding to this one item in this flow chart 351. This force. So we need to understand the force and then all the equilibrium. The equilibrium, and the equilibrium is corresponding to here. And we define the force. Force is the translational force or bending moment, or twisting moment. That's the definition of a force. And then because of this force, internally, there will be some force equilibrium as well. So that's the subject we cover here. And then analysis of deformation. What is the analysis of deformation? Well, we have a subject regarding deformation and what deformation condition. So actually the deformation itself has nothing to do with the force, but the deformation usually caused by the load, but the analysis deformation or definition has nothing to do with the forces. So analysis deformation or definition of deformation is the describe how material will have a deform or change its configurations. So the subject is deformed like this. How can we describe that? or deformed like this, one-dimensional, how can we describe that? We need a precise way of descriptions and describe all the deformations. So this is the older subject, and again, as you can see, every chapter we repeatedly use this 3-5-1 flow chart, so that make sure where we are, what subject we are starting. And so the deformation, let's say we have a certain bar subject to a spring, and then no matter how deformed, there should be some deformation condition. Let's say this bar has a straight and etc. So this is the subject we cover in the deformation that corresponding to a deformation and deformation conditions. Now uniaxial load is the uniaxial loading and deformation. Load and deformation. What's the subject? Load and deformation is like the spring F and Kx. F and X. So it is about K. Load and deformation. So it's a way of defining material property, stiffness. So we will define this all the how we're gonna deform the lengths and cross sections, and then define of stiffness, Young's modulus, and the simple way of stress and deformations, and the stress strain curve. So Poisson's ratio. That's the about the brief introduction of a uniaxial force and deformation. So consider that as the stiffness. Now stress and strain transformation. Oops, this is now is a real subject extended from 1 to 3-dimensional. Forget about the old 1-dimensional structure for now. Even 1 dimension inside there is a 3D configuration. So anyhow, understanding stress, understanding transformation. What is a transformation? We need to understand this important concept. So to do so, we need to define the stresses. Now, as you can see, stress here. Okay, stress here. And then, while inside the material, let's say there is something goes on in at the O, but if to describe what is going on inside O, how can we look at inside? Well, only way is through the cutting, right? See what's going on. So the way we cutting is this way and that way, or the many different way of cutting. So even though there is something goes on, the way we cut, it shows differently. So this is the way we describe stresses at point O. That is a 3D, all the directions. But how we describe that? Imagine the cutting plane to see inside, and now there it can be some internal forces. So that's now the stress concept comes. This is a very new subject, but I'm sure you guys already study a little bit about the stresses in the previous semester. But again, cannot emphasize enough how important this concept is. 3D, the stresses. But 3D is again some force occurring inside the material. It is as simple like that. Okay. And in this chapter, most occur and very technical word, but not so. But point is that don't lose this global flow chart. And there is a inside here we have an introduction of a strain. This is strain. So as you can see that stress, strain in terms of 3D, and we define the stiffness. So we have a strain, and the strain is the way we describe a certain describe how the material, in this case a scale, deform. This one will deform like this. How can we describe? So that's why we need a word, a concept of a strain. Okay, and then since we are covering the stress and strain, what will be the next one? We will study about the stresses and material properties. So you see, as you can see, we start from very simple one dimension and then I extended to a 3D body to understand the concept in 3D body. That's why we need a concept of stress and strain and material property in 3D body. So inside the material, we have stresses and all the now deformation. Imagine this body is deformed and there is something is going on. And how can we describe, how can we connect the concept of the force and deformation? Is very much the same as the spring. F and X, how can we relate? K is the one we relate. That's the very simple external. But exactly same concept is happening or should exist inside the material. So rather than just a F, inside there will be a very complicated, a lot of forces. Again, the way you're cutting, it shows the different forces. So those are stresses. Actually, the 9 stresses rather than just one force. 9 stresses existing in a body. And also this body will deform similarly to the spring in extending. Inside, there is some deformation, right? This much structure will deform like this. Then how can we, that's a result of the internal deformation, right? So how can we describe the internal deformation? Exactly the same concept of stresses. Stress and strain is different, but this is the how we relate this stress and strain, and now we come up with see, we have a 6 or 9 stresses. There should be some symmetry, so we only have a 9. I mean the 6 and 6 strain, and we have some relations. This is the how we describe a material property. As you can see, this one is like the deformation. Rather than F equal Kx, this is a X equal 1/K times force. Very same concept, but rather than just one, as you can see, a lot of components. Okay, and then not only the forces, but there can be some temperature effect. Temperature, due to the temperature, the material deform, right? So we will cover this temperature effect Now, next one is the failure criterion: stress, concentration, fatigue, and creep. And sounds like a very different subject from this one, but they are not. This is a failure means that the strength. So the internal stress will reach some point, the material will fail. But how about the 9 component of stresses? How, when the material fail, those 9 stresses, there could be a lot of combination. How this stress will reach a certain level, and how can we describe the failure? This is the most important concept when you design structures, like a mechanical engineer. Like, let's say you will be a designer of an airplane. You will be a designer of an automotive car, or bridges, or any structures. Now your role is to design a certain structure. That structure will subject to a certain load. That structure will deform certain level. Most importantly, there will be some stresses inside. Well, just for the purpose of safety, you make very big, heavy structures when you make the automotive as a designer. Oh, you want just a safe car. You make the very big, bulky, heavy material. What will happen? You will be fired very soon, right? Why? Because, say, engineer is always relate to design. Design has to be very economic, and design has to, you guys has to understand the physics. So either understanding all the physics of materials, and your role is to design. Well, outside it should be a very sexy, beautiful, and at the same time, it has to function very well. How can you do that? You have to understand. Has to be very light enough. Then it has to be very economic enough. Okay, so understanding of the failure, say failure level is here, stress level here, it never fail. That's a stupid way of design. You just wasting of this material, wasting of all the resource. That's why you're gonna be fired. Limit is here. You as a designer, no matter what's going on, and then you just push this much. What does it mean? You save a lot of material and contribute to society and contribute to the company who hire you. That is the competitiveness of yourself and your company. So anyhow, understanding limit is the key in design. With understanding of stress and strain and what's going on, and then how much load you apply, how much the forces you need to consider when you design the airplane, design automotive. Okay, so anyhow, this is the stress less than strength, but the importantly, stress will be a 9 component because inside, because you have cut this one, or there will be a 3, cut this way, or you have a 3, cut this way, you have a 3. So 9 stress component, even one point. That's why I'm saying that even though there's a 1 point, the way you look at it, meaning that the way you cut it, there will 3 components of stress will appear, forces will appear. So that's why at 1 point we have a 9 components. And 9 components how can they exist not to cause any material failure? Just the function as they should be. So anyhow, now we have a 9 component, we have a strength. How can we design this one? Okay, so that's the failure criterion, and the we understanding the boundless stresses or Mohr circle, Chaska is the criterion. And historically, there are many, they are also same engineers like you. But they do an experiment, a lot of experiment combining combination, considering all the nine the stresses. And then they found a certain rule. Oh, the 9 component stress, they reach a certain way, it fails. So it helps us a lot. We don't have to go through all the experiment. We don't have to spend a hell of time. We just follow the rule. So that's the failure criterion. And depending on who developed and who found Van Mises, Tresca, even myself, I have my own failure criterion. You can do that. Now you have a very different material. You can come to your own failure criterion. So anyhow, this saves us a lot of time and effort. And then chapter 8. So we almost cover all the subjects. And as Barry introduced in the very beginning, we just like to design a shaft. What is a shaft? We have a one-dimensional on the torque. So shaft and torsion. And then we are applying all the steps and theory to better understand how to design this shaft. So this is going to be a chapter 8. Again, this 351 appears again. Why? Well, it's clear now. Even though this form of the structure, the way you apply the load is different, but the concept flow will be the same. So we're going to study all the theory and geometry, but I'd like to emphasize that don't forget this 351 concept. Okay, that is all about the torsions. And the, for example, we have a 3 shaft, connect. And then there is some left-hand side and right-hand side. We have a fixed. Now we try to solve, we apply the load here. What is the load? Torque. This is the a kind of one simple case we can consider. And this is where we can solve this problem. Imagine that. What is a force? Force is this guy, torque. Now we understand this torque. And then material, well, we need to understand all the stiffness, this one, that. And then what is the deformation? Deformation condition on the right-hand side and left-hand side, we have a fixed. So this is a given. Now we try to solve how much it rotates, depending on the cross-section, depending on the material properties. And to solve this one, we need to understand what is going on inside. Equilibrium, how much stress, and how it rotates, and stiffness, and so on. And then make sure all the stress is less than strength. Okay, so it looks like a very advanced subject, but it's clear that we follow this one. Now I'd like to emphasize one more very important. See, when you study certain subjects, even in solid mechanics or fluid mechanics, rather than just a mathematical description, now you should be able to define this problem from real world. That's the very important, that's the way you have to study. Rather than just in the high school, you are given some mathematics to solve, differential, whatever, and then you just solve. But now you as a practical engineer, you should be able to define the problem from the real world. Okay, so let's say what kind of problem it can be like this. Say some say automotive. Well, nowadays all electric, but it doesn't matter, electric or internal combustions. You have a certain say the structure like this, and you have four wheels, and then there could be some engines, or some forces can be from the motor or whatever. So all these shaft is a driving shaft will be subject to a torsion, because there will be some driving force from internal engine or movement, the motor. And this shaft will transmit the torque, and then all this vehicle will move, right? So, well, it doesn't look like exactly the same, but the point is that, this older shaft, driving shaft, now you understand why they are called shaft, because this structure transfer or subject to torque rather than bending. It's a torque. So as you can see, torque and shaft is one of a critical structure in a car. So and then all these things can be modeled like this. Again, my emphasis is like this. Now you as a practical engineer, rather than solving this problem, you should be able to define this problem from real world. That's a real mechanical engineer. That's I hope you understand. Of course, there is some practice and training, but always keep that in mind. Whatever you see out there, out of class, you should try to keep thinking about the real world. How can we solve, how can you design structures, components, using the knowledge you are learning in class? Fluid mechanics, well, there's always an airflow out there, and cold and hot, what's happening, and then how can I describe using the subject you learn in the class? Same here, solid mechanics, we cover the certain physics, but again, your main role is to bridge gap, real world or mathematics. We are covering mostly how you describe, how we solve this mathematics, and then how this mathematics comes from, but please keep that in mind. Okay. That's what the AI cannot do. So you should get along with AI, but you should find your own role. So anyhow, okay. So the next one, very complicated, a little more complicated, but don't forget, complication doesn't mean a different theory, same concept. So all the way through a shaft and then another shaft, but this time we have a little thin cross section or long, slender, and thin structures. Why this structure can be important? Why we need to study about this one? Well, the wing airplane, uh, see, I'm sure you've been traveling with the airplane on, and then the airplane structures will uh, react to all different types of a load. And when you fly, these structures, the wing especially, subject to the vertical load, and of course it bend, but it's importantly it twists as well. Very important. So the cross sections of a wing is now, as you can see, very thin wall structures. Wing of aircraft is not a solid, it's empty in there. Why empty? Well, the outside geometry is nothing but control airflow. Airflow difference, velocity difference, cause of pressure difference, that is the force we lift up. So it doesn't need to be solid inside because the air doesn't go inside, air flow outside. So outside the structure is important, and to make the structure light, inside the empty. But again, this structure is subject to torsion. So that's why we call them thin structures, and how they react to the external load is the very classic but very important subject. Not only just the airplane, but also say wind turbine. The wind turbine blade, the renewable energy source. While we try to meet wisely this climate crisis using the more of renewable energy rather than just petroleum based. That's one of the big contribution we can do as an engineer. How can we make use of this natural non-CO2 emission energy source? Wind turbine blade, how this is rotate is not the simple way. It's not the I mean, it has a flow and structure. Imagine this, how large or how big this one blade is. 100-meter long, just one blade. One blade. Well, I'm not sure you visit the United States, but this is the Statue of the Liberty. But you know how big it is. But compared to this wind turbine blade, this is a little tiny statue. How big you can imagine that. And you imagine how big this one blade. Well, this is the I want to show you how this is a people standing here and looking inside, and imagine how large it is. And then all over the world, especially China or Europe's, the blade is getting bigger and longer. It's huge. And imagine this is rotating just by the wind. So wind will rotate this guy, and then inside there is a big generator. Generator is rotating and generate electricity, energy. So simply wind give us electricity. You know how important electricity is, even in these days. AI was most important, while smart and algorithm, while more importantly, the energies. Demand will exponentially increase. So you as a mechanical engineer, you can have many dreams, or you have visions of your future job. Energy is the one very bright and very wonderful job area. You can apply your knowledge of a mechanical engineer, and also very rewarding area. So no matter what you do, please keep that in mind, the energy. So anyhow, this is the energy conversion device from wind to electricity. And also, I mean, you name it. Most of the structures are subject to, now you can see that wind is applied to a wind turbine blade, and wind turbine blade will deform. Wind turbine blade in our world is the material. Wind will be the force, and then blade will be deformed. Of course, it rotates as well, but most likely it's deformed. How much deformed? A lot. So sometimes when it deforms, you know, there's always a tower, and there are three blades. So blade deform too much. So when it rotates, this tip of the blade, it hit the tower. So that's the one of a constraint or one of design factor you need to consider, how you deform. So this is the when you design, you should not let it deform too much. So for that purpose, you need to understand all the theory, stresses and strain, and then material property, and so on. And also this beam and torsion. So anyhow, I just would like to emphasize the what we do is not the subject in the lecture note. This reflects the real world. So anyhow, all subject of a torsion. After that, we have a beam theory. What is a beam? Again, beam is the one, let's say we have a one-dimensional, like imagine the wing subject to a vertical load, it will have a deform. Deform? Yeah. Well, twisting or torque, you twist, but it is deform. And all kinds of a load. Now load is a rather complicated. Complicate doesn't mean unable to solve. We just have different types of a load, distribution, vertical, concentration, and moment. So we study all the subjects to cover the beam theory. See, again, when we emphasize this one, all the steps will apply, very importantly, the theory we are checking or considering step by step. So even in torsion or bar torsion beam, we go through each subject, equilibrium, and the stress strain and all the subjects, and combine them, we got certain rules and theory. So that is the one we are using design. And then, of course, again, another beam theory. Beam is the kind of a lengthy subject. So we have a two division. Chapter 11 now is a deflection due to a bending. So we cover, drive the equation. But in doing so, we also follow these 1, 2, 3, 4, 5 steps. Okay? Trust me. Yes. This is the subject we will apply to a different subject. Actually, the literally all the structures, same principles. So don't get, say, don't feel that it's complicated. It's just a very simple 3-5-1 concept, and especially this 5 flow is a control, giving us all the principles which governs what is going on inside. So this is a beam, and then with this one, now we are able to say very complicated, and I don't want to say complicated, this kind of a behavior. Say 2 beams cross, and then we apply, and upper beam will deform and lower beam will deform. Very tricky problems, but there could be something going on in the real world. And now we define like this, we should be able to design how much the maximum load we can apply, not to cause any material failure. Okay, this is the one practical problems. And there could be some issue in the beam theory. So beam, we assign 3 chapters. So understanding beam is the core essence chapter in this semester. Okay, so beam, we have you need to understand the beam moment of inertia. Have you heard that? You've been through this subject, moment of inertia in statics, right? And the shear center, all complicate, kind of complicate, and the buckling is the one advanced subject, and beam will be a subject to not just the bending, but the axial compression load, different from tension. Compression always the structure as the unstable. Unstable means that, you know, when we have a structure, we can have a tension, torsion, bending, right? But very interestingly, we can apply compression. What will happen? Compression, this structure will buckle. It can buckle this way, that way. That's the can happen real world. This is the also should be covered. And the last chapter is the energy method. Energy method is the one which will move us to a next step. say, all the numerical simulations. Numerical simulation means that, say, now these types, now you can model using the computer, starting from the CAD and understanding of a material and understanding force. You can apply the all kinds of a load, and uh, you can really simulate what's going on in car structures. We call white body, and then all kinds of turbines and blade, and the even design of a helmet protecting our head, our brains. I mean, you name it. Almost every physics, every structures, everything, what is going on is based on solid mechanics. But solid mechanics, we only cover a very simple structure. But again, all the concept is here. Now understanding, we move to a next step called computer-aided engineering, CAE. And then now you can use the computers and then be able to real engineer. But without understanding all the fundamental subjects which you cover in this class, we cannot reach here. So, for example, Hyundai, they are automotive. They need a CAE engineer when they need they want engineers to design or airplane. I kept emphasizing automotive or airplane, but that is the just very small application of mechanics. It's a huge out there. Even your cellular phone design, you drop it, or subject to very hot, and what's going on in the chip. Everything, all the stress and deformation will be governed or follow the same rules as a 351 flow chart. Okay, so this 351 covers almost all the physics of whatever, even your tablet and computers, what else? See everything. Okay, so so again, to do so, I mean, understanding the theory of this under CA engineer, we need to understand additionally energy method. Okay, that's the all I like to emphasize today's class. Okay. I want to create a project, ChatGPT, and then I don't know how much this guy can help us, help me to deliver the class, the content efficiently to those who I'm the student. So whatever I do, I will just save here. I can define the subcategories. For example, sorry, I think it's not easy to. Okay, my question, I just want to communicate with ChatGPT. What point should I emphasize in the first class of solid mechanics? He knows me as a professor. Let's see. Sorry. Okay, for the class of solid mechanics, it is important to set the stage by giving student a clear sense of purpose and scope and motivation. Well, I didn't give you, did I give you enough motivation? Well, I hope so. You as a mechanical engineer with understanding of solid mechanics, you can do a lot. Before driving into equation, I didn't drive into equation yet, right? So why solid mechanics matter? Solid mechanics, there should be some important sense, students a clear sense of purpose, scope, and motivation before diving into equations. Here are the key points that should emphasize. One. Bridges, cars, aircraft, ships, pressure vessels, and pipelines, hydrogen tanks, your special setup, OTX, material science, what Taylor can do, the engineering design, what the structure must be. Oh man, sorry, it's you can continue. Oops. Will it last? Continue to improve reliability. How safe is it? Safety factors uncertainty. This motivates students to appreciate the balance between safety, performance, and cost. 3. Basic concepts to introduce immediately. Forces, stress, and strain, the language of solid mechanics. The idea of equilibrium, forces and moments must balance. The importance of constitutive relations, how materials respond. Scales for atomic bonds, material properties, structural response. Okay, well, anyhow, very much same as we covered today, right? So we are in good shape. Well, we just the phone. For the first homework in solid mechanics, the goal should not be heavy calculation. Okay, I agree, and you agree as well. Instead, you should build intuition, connect to the daily life, engineering practice, and refresh pre and homework 1. Okay, this is the homework 1 assigned to you. Part A, observation, conceptual, no math at first.
영양성들 얼마나 없었고요. 주변에서 볼 수 있는 뒷발작전, 다리 문자, 스마트폰 프레임, 수소통의 신발 이상을 선택하세요. 각 구조물을 때 다음을 간단히 서술하세요. 이게 가장 큰 문제로 올 것 같습니다. 이 결격되는 파손이 발생하여 사용자 제어와 문제와 수업비용 그래서 우리 세상 제어와 구조를 시작해요. 이 모습 맞아요. 정의라는 제로 기초하는 단순 보에서 양쪽에서 진행되는 기간이 중요한 소통을 유지하는 지적 관련을 계산하시오. 이 운영 기본 문제, 단편적인 시민 확대와 선 매니저를 관리해 맞대의 범위 것을 계산하시오. 선수와 인력학회의 모습 자연스럽게 시킵니다. 짧은 글쓰기, 역사적 사료자, 주제인 왜 기계 유도 제도가 있습니까? 세우는 모습.
Okay, well, that's the same, almost same homework I like to assign. So I just link here. You can click and you can see what we just covered. Okay, that's the subject I like to cover today. I hope that as an introduction, I hope that this is not too heavy. But well, what the heck, class cannot be that much fun. But I'm trying to make it as easy as possible and to draw your attention. But that's my effort. But from your side, you should have some effort as well. I know it's not fun. Again, you should make some effort. Try to concentrate. Try to understand. This new subject will not come to you easily, but with your effort, okay, with your effort, you reach some level, and then you will enjoy a lot. It's like the video game, playing game. 게임들 여러분 좋아하죠? At the very beginning, it's not so much fun to enjoy the video game. Why? Because you don't know rules, you don't know how to play, and so on. But you make the several effort to learning and get used to it, man, you can really enjoy that. The exactly same. Well, gaming or understanding something, what the hell is difference? Same. So you make the initial effort to reach yourself at a certain level, then you can dive into enjoyment of learning. Wow, you will be amazed. And then you will be also proud of yourself being one of the excellent engineer. Every company will look for you. Okay?